project title is The Seven Bridges of Konigsberg. Network has become a common part of our lives today, and we often hear the term computer network, social network, and transportation network throughout our life. All these terms have their origin from graph theory, which itself originated from the Konigsberg Bridge problem. Now let us view this interesting puzzle. Konigsberg Bridge problem was a historical problem of the year 1736, and Konigsberg was the capital city of East Russia, and a river named as Prigod River passed through this city. This Prigod River divided the city into four land areas A, B, C and D, where A and B are islands and C and D are banks of the river. All these four land areas were connected by seven bridges. At those times, residents used to wonder whether is it possible to start from a land area, move through all seven bridges exactly and come back to the same area. Many residents tried this activity, so let us also try this activity. Starting from land area A, let us move to bridge number 1 and to reach island B, A, and bridge number 3 to reach C, and D. From D we have to move through 4 to reach island A, and 2 to reach island C. And here we can see that now we have to move through bridge number 6 to reach island B and 7 to reach island D. In this case, we can see that bridge number 5 is missing, and we can't end up in the same starting point. This problem was common among the citizens, so they went to a Swiss mathematician known as Leonardo Euler, who solved this historical problem in the year 1736, which gave the first concept of graph theory and the first proof of network theory. Euler converted this problem into a graph. Graph means collection of vertices and edges that join pair of vertices. Vertices means points and edges means lines. Here the Euler represented these land areas A, B, C, D as the vertices and the bridges by the edges. Now the land areas A and C are connected by two bridges, so we draw two lines between A and C. A and D are connected by two bridges, so we draw two lines between A and D. The island A and B are connected by one bridge, so we draw one line between A and B. The C and B are connected by one bridge, so we draw one line between C and D. D and B are connected by one bridge, so we draw one line between D and B. This is the graphical representation of that model. This graph is known as connected multigraph. Connected graph is a graph there is a path between every pair of vertices. Multigraph is a graph that has multiple edges to connect the same pair of vertices. Konigsberg bridge problem is same as draw this graph without lifting the pen from the paper and without retracing any line and coming back to the starting point. Now let us try. If we start from the vertex A, 2C, 1A, 3D, 4A, and 5B and 6C. Here the bridge 7 is missing. The starting point is A and the ending point is C. So we couldn't complete this circuit. Now let us try from the vertex B. If we start from vertex B, 6C, 1A, 5B, 7D, 3A, 4D. Here the bridge 2 is missing. The starting point is B and the ending point is D. So finally, Euler concluded that this problem has no solution.
Now let us see the reason for that. Imagine if you enter this house through this way without using this way you want to leave. Means it is only possible if you have another way. In this problem, all the land areas are connected by odd number of bridges. In graph, all the vertices are incident with odd number of lines. The number of lines incident with that vertex is called as the degree of that vertex. The number of line from A is 5, so the degree of A is 5. The number of line from B is 3, so the degree of B is 3. The degree of C is 3 and the degree of D is 3. So all the vertices are of odd degree. So it is not possible to draw the graph without lifting the pen from the paper and without retracing the lines and coming back to the starting point. Now we have a question in our mind. How to draw a graph satisfying all the above conditions? Yes, if we convert all the vertices into even degree, it is possible to draw the graph. Let us try to add some more bridges to complete the graph. If we add the 8th bridge in between B and C, the degree of B becomes 4, which is even, and the degree of C becomes 4, which is also even. But the degree of A is 5, which is odd, and the degree of D is 3, which is also odd. Now in this graph, exactly two number of vertices are of odd degree. In a graph, if exactly two vertices are of odd degree, we can cover all the edges once, but the starting point and the ending point are different. This graph is called as Eulerian triangle. If we add the 9th bridge in between A and D, the degree of A becomes 6 and the degree of D becomes 4. Now all the vertices are of even degree. So now let us try to complete the graph by A3, D4, A1, C2, A5, D6. Now I have covered all the vertices 1 and came back to the starting point. This closed figure is called as Eulerian circuit. If we add one more bridge to the solution, we can get an Eulerian pair. If we add two bridges to the solution, we can get an Eulerian circuit.
The Konigsberg bridge problem may have started as a simple curiosity, but it gave birth to graph theory, which is a powerful field of mathematics that forms the backbone of today's computer network, chemistry, physics, Google Maps, social science, etc. This shows that how one small problem opened the way to great ideas. Beyond mathematics, it reminds us that curiosity and exploration can spark discoveries far greater than we ever expect. Using this concept, we have designed a game. The player can start from any one of the room. Then player should collect 5 coins and come back to the starting point. Under the condition, use the edges exactly once. For example, I am going to start from this room. I am choosing this way and I am collecting the first coin. And going in this way and collecting the second coin. And going this way and collecting third coin. And going to the fourth room and collecting the fourth coin. And going to fifth room and collecting the fifth coin. And I choose this way and come back to the starting point. This is the Eulerian circuit. Under the concept of Eulerian triangle, if we start from this odd degree room, we will collect all the coins. But we will finish the game at another odd degree room. Under the condition, use the edges exactly once. For example, I am going to start from this room. I am choosing this way and I am collecting the first coin. And I am going in this way and going to second room and collecting the second coin. And coming in this way and collecting the third coin. And going to fourth room and collecting the fourth coin. And coming to the fifth room and collecting the fifth coin. And going to the sixth room and collecting the sixth coin. And I am choosing this way and going back to the another odd degree room. Can you please try this game?